Good morning. It's a great pleasure to introduce Miguel Walsh, who has revolutionized certain areas of additive combinatorics. So there's a long history dating back to Furstenberg, taken over by many people, including Ben Green and Terry Tal. Some of Miguel's work, which maybe he'll describe to us, is an extension of the methods which worked initially in ZD to nilpotent groups, and I think this has created a great deal of excitement. And so I think I feel it's highly appropriate that Miguel should be honoured with the prize that he's been offered. So Miguel.
Thank you very much. Okay, thank you very much, Anthony, for the introduction. And I had some problem preparing this talk because, on the one hand, I feel that there are some results I should mention today. On the other hand, one always wants to talk about one latest result. So that was not the only problem. The other problem was that yesterday I was presented as an ergodic theorist, and my original plan was to give a talk that has absolutely no ergodic theory in it. So here's the compromise. I'm going to talk about some results in ergodic theory, number theory, the affine geometry, which I think they are easy to understand, so maybe you can take them home. And they have one common feature, which is that in some way they exhibit this remarkable phenomenon of discrete rigidity. So let me say a few words to try to explain what these kind of discrete algebraic structures are. So in many problems in mathematics, it is usually the case that one wants to show that some specific object of interest behaves in a random manner, behaves like one would expect probabilistically. So that is, in many cases, a good intuition, and in many cases it is rather easy to prove that most objects behave in a random manner. But it may be very difficult to prove that the precise object that you're interested in behaves in this random manner, or maybe that all the objects behave in this way. So it is a remarkable phenomenon in many problems around number theory, let's say, that, I mean, these problems are very hard because you have no reason why they should be true. I mean, you believe in them because there is no reason why they shouldn't be true, and it's the thing that usually happens. So, but it is very hard to prove something that you have no reason why it is true. So it is a remarkable phenomenon that many breakthroughs have been made in the last years that go in this way. They realize that in order for something to behave very different from the random behavior one expects, they actually have to exhibit some kind of algebraic structure. And not just any algebraic structure, but some discrete algebraic structure, in the sense that you approximate your problem by discrete objects, and this is the uniformity of the algebraic structure you get that actually is very important. So actually, when you think about your problem, you can say, well, my object does not look like this algebraic structure, so in fact it has to behave randomly. It's a very interesting phenomenon that I will try to give you some examples in this talk. So let me begin, yes, with ergodic theory. So as I said, I think the results are easy to understand, but in the case of ergodic theory, there is a context, basic context, that has to be set. So we will work with X mu is an arbitrary probability space. And so X is in space, and mu is a measure of, well, the measure of the whole space is 1. Then, in ergodic theory, you want to study how things behave under the action of measure-preserving transformations. So you're given T, T1, TL, measure-preserving transformations of your space, and you want to, in general, understand how the orbit of points along these transformations behave. And we will always work, at least in the discussion of ergodic theory, with functions in L infinity, bounded functions, mainly because it is the assumption you need in order to make sense of the questions we want to discuss. So the basic theorem, arguably the basic theorem in ergodic theory, is von Neumann's mean-ergodic theorem. This says that if you take the classical ergodic averages, so you take some function and you take some measure-preserving transformation, and you make the average of this function along the orbit. So this basic theorem tells us that these averages always converge in the L2 norm. This is one of the fundamental results of ergodic theory. So non-conventional ergodic averages are about understanding how far this can be generalized when dealing with several functions or several transformations, how much of this kind of rigidity holds. So, yes, we want to generalize this result, and there are many ways in which we can generalize it because we have many transformations, we have many functions, we can play with them. So, a basic thing we can do is to consider iterations of this transformation. So you have one function, but many transformations. You apply one transformation n times, the second one n times, the so on, n times, and you average what you get. So this is maybe the easiest thing one can do, but probably the less interesting of them. Much more interesting, I think, is when you have multiple functions. So you have several functions, and you also have several transformations. And each function, you take it along the orbit of the corresponding transformation. Why I think this is much more interesting is because what you're talking about here is correlation between functions. A lot of problems in combinatorics number theory can be reformulated as questions about correlations between interesting functions. So here you want to understand how these things correlate along different orbits. So to give you an example, the famous result of Semeredi about arbitrary long arithmetic progressions in the integers can be stated simply as that the integral of an average like this in a very particular case is positive. So, in the limit, right? So you can do that, but you're restricting to very specific things. You're iterating once at a time. Why should I do that? So in generally, I can replace the value n here by any polynomial. So why polynomials? A good reason is that you cannot take anything there, because if you take anything, you can just play around this thing any way you want and make it behave badly. You need something that actually preserves the rigidity of these kind of averages. So it turns out that the polynomials are the right thing to look. They have the kind of structure you need, and in fact, in many senses, you need them to be polynomial. But so you need that assumption, and what you want to know is what conditions do you need to guarantee that these things always converge. So you want conversions to hold for any choice of bounded functions, like in the von Neumann's theorem. So you want to impose conditions on your transformations. So what you do, of course, is you look at the group generated by these transformations, and you want to know what conditions you have to impose on this group to guarantee conversions. And the conjecture was that conversions will always hold for any combination of all these kind of things. You can play around any way you want with these things. Conversions will always hold as long as the group is nilpotent. Now, the assumption of nilpotency is very important in all these discrete algebraic structure phenomena. There are a lot of results whose hypothesis is that the group is nilpotent. The reason that is because nilpotent groups are exactly the kind of groups that preserve algebraic structure. So you can define polynomial mappings from any group to another group, and it turns out that they preserve the properties you expect from polynomials precisely when you're dealing with nilpotent groups. If you have something that is less than a nilpotent group, you will probably lose all your algebraic structure. So the first result is the following. It says that as long as G is a nilpotent group, in fact, every combination you can make of the above directions always converge in the L2. So let G be a nilpotent group of measure preserving transformations of your space, arbitrary space. Then this general averages, so you're averaging here, you're averaging here over n, and here you're taking a product over several functions, and you're applying your transformations any way you want, and your polynomials, you can choose them. They depend both on the transformation and the functions, so you have complete freedom to play around. And these general things always converge in L2 for every choice of transformations in your group, for every choice of bounded functions, and for every choice of polynomials. So this was conjectured in the abelian case by Furstenberg, probably more general, but the statement in this more general case is due to Bergels and Leibman. And this result was open in the Furstenberg, in the abelian case. So let me tell you some known work towards this. There is a very famous result of Host and Kra, with a different proof later given by Ziegler, which says that the average is when you have one transformation and you go along an arithmetic progression, these things always converge in the L2 norm for every choice of functions. So this will correspond to a cyclic group. And it is a very interesting particular case because it is actually the case that corresponds to Semiramis' theorem. And in fact, they do more. They actually tell you that the limit is controlled by a system, by an inverse limit of nil systems, which is a technical thing, but it's actually very useful in practice. So another result, again, you take the same transformation, but now you have something that is nonlinear. In this case, this kind of averages, t to the n squared, was dealt by the work of Furstenberg and Weiss in '96. They tell you that these things always converge. It is very interesting because it's the first nonlinear result, and it's the first place where the concept of a characteristic factor is formally introduced in the literature. It's a concept that is very important in ergodic theory. And although we will not need it in our proof, in some sense it is some reflection of this discrete algebraic structure in the infinity. So we will deal with a purely discrete algebraic structure. So another result is by Berghaus and Lehmann, which tells you if you take the simplest possible non-conventional ergodic average, then this does in fact converge if your transformations generate an nilpotent group, but they do not necessarily converge if they generate only a solvable group. In fact, they show that if you have something that has exponential growth, then you can always find a pair of functions such that this does not converge. So again, one way to think about this preservation of polynomial structure by nilpotent groups is the famous theorem of Gromov, which tells you that groups of polynomial growth are exactly the virtual nilpotent groups. So it is a very, very usual phenomenon, and not only there, I mean, even in ergodic theory, you have in homogeneous dynamics, you have that usually you have to place some unipotent assumption on your theorems, which is essentially the same thing as saying that the group having a nilpotent group, which for in the theorems of Margulis, more generally of Radner. Or even if you deal with approximate groups, this theory, these conjectures of Lindenstrau and Helfgott that were answered qualitatively by Broglie, Green, and Tao, also need the assumption of nilpotent group. It's the right assumption to make. So, and this result of Tao tells you that convergence holds if the group is abelian and every polynomial is linear. And this case is particularly important for the general result because it was the first place where these characteristic factors were not used, and instead finitary methods were employed. So although the general proof of convergence for any nilpotent group is not of a finitary nature, it does use concepts that are much closer to these ideas of Tao, of looking at uniform discrete structures. So here's again the general result. And well, I'm not going to discuss the proof, but let me tell you just what these steps, just names for the steps. So the proof has 3 parts. The first part is about doing a decomposition of your function that you're studying into a structure part that manifests this kind of algebraic structure I'm talking about without being very clear, and a random part which behaves always very nicely. So this is, the compositions are very abstract. They work they're decompositions that work for any Hilbert space. They're very general things and very useful things. So you can do that. And I'm not going to talk about them now, but I'm giving a talk in a couple of hours in the dynamical system session where I'm going to give much more detail about the first part that uses very beautiful ideas of Gowers. And again, it's very useful because it gives this idea. You take the random part away, and you just have to deal with something that is very structured. It simplifies things. So the second part is, well, you know the random part behaves very nicely. You can take it away by the decomposition, but you still need to define what your structure is. And that depends on your specific problem. So I'm going to say a little bit about what the structure is in this problem because it's where this discrete algebraic structure appears. So for now, let me tell you that the structure part, when you apply the transformation, it makes your system look like a simpler system. So maybe you apply something that goes along something nonlinear to a function that is very structured, and it actually looks like something linear, which is much simpler. So I'm going to say something about that, and then what you do, once you know that you take you take any function, you take the random part away when you do the decomposition, because that behaves very nicely. The structure part is something that is very rigid and reduces to a simpler system. And then, of course, what you do is just make an induction that you reduce until you get the trivial system where the result is just trivial. So the induction is technically demanding, but the ideas are not there. So, although it uses some very nice theory of Liebman, of polynomial actions. So, let me tell you a little bit, very little, about what the structure is in this problem. So you can see that actually the structure in this problem that has, in its nature, has nothing about discrete things. It's just a problem about, in the limit, what you know about these averages. But it's very interesting that you can control this thing by discrete things. So suppose, let's just consider this very particular example. You have two commuting transformations, and you make this average, right? You go along one transformation, you take the squares, along the other one, you go linearly. So again, you have to define your structure. You don't know what the structure is, and it's very strange that somebody will look at this and guess what the structure can be. On the other hand, it's remarkable that we have very good intuition for what randomness is. So if I say, for example, that the function f1 is random, in general, one imagines a function that is oscillating widely, and then one expects that a lot of cancellation has to occur. So if f1 is a random function, I expect that this, when you go along the squares, this will behave so randomly that there is no way that something as structured as another orbit can actually see it. So if your function is very random, I expect that after you make the integral of this, for example, this has to go to 0. It has to make so much cancellation that it has to go to 0. So if it's random, it's exactly what we want. It converges to 0. So this is a little bit weaker. It's simpler, but weaker that the integral goes to 0, not the But this is weaker. We want to understand the opposite behavior. So it's very nice. Random, you know what it is. It just has to go to 0. It's very intuitive. Now you define the structure. The structure has to be the opposite of the random part. So you just say what happens if the opposite of this random behavior occurs. So what happens if for some very large value of n, I know that this integral, in fact, is bounded away from 0. So suppose f1 is such that this average, the integral, which is in fact weaker than that one we need, but it's simpler, this integral is greater than some epsilon for some very large value of n where you wouldn't expect this to happen. So what happens? So here, of course, you will have to take me on faith, and if you don't want to take me on faith, you can come to my talk in a couple of hours. So easy calculations, they're quite easy, show that in fact f, in an appropriate sense, has to behave like this average over here. So your one function, yes? It's okay. So some easy calculations show you that in an appropriate sense, f1 behaves like an average. So you have one function that behaves like an average of several functions, and that is very nice because in general, an average of things may behave much nicer than just one object. So you have it behaves like a very large average because n was very large. So if you pick a small value of h, and you move the average that was in this large box of size n just by h, you move it just a little, then the average will not change much. So what this implies, what this will imply that your function f1 has some kind of invariance properties under transformations because it behaves like a big average, and a big average does not change much if you move it a little. So it's giving you some property. And, well, one can deduce from this that, for example, so f1 will look like this big average, and look that over here, h appears just squared here, right? So if you apply t1 to the h squared to f1, you will just cancel this out. You will have a big average of linear things, but it is a finite average of linear things. And a finite average of linear things will also look linear. But this is just not true if you do not care about this kind of discrete algebraic structures. So in the end, again, I will give details in my other talk. What you do is that if f1 is the contrary to random, it has this rigidity, this algebraic rigidity, that if you apply a certain polynomial transformations, it actually is controlled by simpler polynomials. So this average, which was originally nonlinear, will behave like a linear system. But it's very important that this discreteness is very important because you need uniformity. You need to know that you can have finitely many averages and you can control them uniformly. This kind of deduction that you can make here, you cannot make if you just take the limit, if you forget about the discrete structure. So you go to a very large value of n, take the structure there, go back to small scales, and you do this little trick that you cannot do in the limit and gives you information that otherwise will have been lost. So again, I will give more details about this in my other talk. So now let me turn to another phenomenon where this discrete algebraic structure is more apparent. So here it's a very nice tool to see what you can do, this kind of discrete uniform control, but now it will be the main problem. So we turn to a problem in number theory that I'm very fond of. So write n just for the first n integers, n to the d is the cube formed by the first n integers in each coordinate. And a central problem in number theory is to understand the distribution in residue classes of special sets inside this cube of interest. So for example, well, one basic interesting example of this are the primes. It is not just interesting that understand how well primes are distributed in residue classes, but in fact this is maybe the most powerful tool one has to understand general behavior of primes. And a very good example of this is the recent result of Zhang, a spectacular result of Zhang, that tells you that there are bounded gaps between primes infinitely often. Tremendous result. And the way he proves this, and it's a way that everybody knew that something like this will suffice by previous work, is that he shows that the primes are a little bit more well-behaved in residue classes than what one already knows. I mean, by the generalized Riemann hypothesis, one can deduce some kind of good behavior, and that, in fact, is known unconditionally on average. This is a result of Bombieri and Vinogradov. And Zhang tells you, well, in fact, they behave even a little bit better than that, and that, by known results, implies that there are bounded gaps between primes. The reason why studying things in residue classes is very important is because, in some sense, it's giving you like a Fourier analysis. It's like knowing how it behaves in each class. It's like knowing the different Fourier coefficients of a function. There's a lot of analogy with that. And in fact, today, Rodriguez Villegas gave a talk where he actually made some points like this. What you do when you look at something mod p for many primes p, you're looking at the same object from different point of view, and then you can take all this information together and gives you very strong information on your original objects. But of course, not all in primes, but for example, algebraic variety is the distribution in residue classes. In the case of curves, is knowing the exact distribution each mod p is the Riemann hypothesis over finite fields. In general, it's the Lang-Bain inequality. So it's a very interesting thing. And again, in general, for example, for the primes, one wants to see that they are very well distributed in residue classes. That will be optimal. And in fact, we expect that a random set should be very well distributed in residue classes. So this is again an example of a problem where you expect your object of interest to behave like most objects do, but it's very hard to prove that your object behaves in this way. So in fact, we expect a random set to be well distributed in residue classes. In particular, we expect it to occupy essentially all the possible residue classes. We do the reduction. In fact, it is, if you think about it probabilistically, it is very unlikely that a set will occupy very few residue classes. But as a matter of fact, there are a lot of examples of sets of that kind. So there are examples of sets that are very badly distributed in residue classes. The most classical one is the set of the squares. If you look at the squares, right, 1, 4, 9, 16, 25, it is well known, it's an old result, very old, that S occupies only p plus 1 over 2 residue classes mod p for every odd prime p. And so that's very strange, just half the residue classes. If you think there are a lot of primes, so occupying half the residue classes for each prime is very strange. But the squares do that. This is a trivial example. When you go to higher dimensions, examples are more trivial. For example, just take the diagonal. Then this is a big set. But of course, in 2 dimensions, you have p possibilities for the first coordinate, p possibilities for the second coordinate when you do the reduction on p. But this is just the diagonal, so they are just p residue classes of the p square possible residue classes. So trivially, this is a very badly distributed set. And in general, as I said before, we know that the solution set of a polynomial equation of low degree occupies very few residue classes mod p for many primes p. For most primes p, this is a precise estimate is given by the Lang-Bain inequalities. So in fact, you see that all these examples have clearly something in common. They are all very algebraic in some sense. Maybe not in the same sense, the squares and the solution, that one is the image of a polynomial, other is the solution set, but they are very algebraic things. And again, the study of the distribution of things in residual classes is a very old, interesting subject, and it is a remarkable phenomenon that only some years ago, it was formalized, the basic conjecture that maybe you are all doing right now, which is called the inversive problem, because it has to do with SIB theory, which tells you the following. If you have a set that occupies few residual classes mod P, and let me make two remarks. When I say that occupies few residual classes, then you can replace this by saying that it is badly distributed in the L2 norm. It's just to make things simpler. It's just that it's badly distributed in residual classes. And the other remark is that when I restrict myself to primes, it's just because once you know it occupies few classes for primes, you know it occupies few classes for every other integer. So suppose you have a set that occupies few residual classes mod P for many primes P, then there are just two possibilities. Either S is small. I mean, if you have a very, very small set, it is obvious that if you make the reduction mod P will be very, very small because your set is very, very small. So either it is for a trivial reason, either it is small, or S has to have some algebraic structure. And again, the distribution in residual classes is a very useful phenomenon, so it is quite remarkable that, you know, there is a reason why something is very badly distributed in residual classes. It has to have algebraic structure. But there is a problem with this formulation, which is, well, you say that the set has to be small. SIB theory, which is a very powerful tool of analytic number theory, already tells you that the set has to be somewhat small. So maybe you're not saying much more with this. And on the other hand, what does algebraic mean? I mean, any set is algebraic. You can take any set and it will be the solution set of a polynomial equation of sufficiently high degree. So maybe this is meaningless, so the right conjecture is this one. So we have a set that occupies very few residual classes mod P for many primes P, then either S is very small, much smaller than what SIB theory tells you. So you can, in fact, improve the bounds. When you have a problem, you have much better bounds than you had before. Or your set is very algebraic, which means that not only you have a polynomial, for example, vanishing on your set, but the polynomial is of a very small degree. You can really have a uniform control on the degree of this polynomial. It's a strong kind of algebraic structure. So this is the problem. And this conjecture was formulated by Krut and Walsh in a special case, and in general by Helfgott and Venkatesh. But in fact, they all said, well, this conjecture, it's rather obvious. So the conjecture of Helfgott and Venkatesh is much more general. And as I said, SIB theory shows that S cannot be too large. So when D equals 1, and under additional hypothesis, there are recent results of first Ben Green, then refined by Schoenberg-Gain, then refined again by Adam Green and by Ben Green and Adam Harper, that imply that S, in fact, has to be very small. But the additional hypotheses are, in fact, you're saying that it is like this. Your set, the hypothesis says something like your set is very, very different from being algebraic. So if you know that your set is very, very different from being algebraic, some specific hypothesis, then you know that S has to be very small. But the first place where this beautiful dichotomy was exhibited, where you actually show that either it is small or in fact you have a polynomial, you have algebraic structure, is this result by Helfgott and Venkatesh in 2005, where they show that this phenomenon holds, this duality, this dichotomy holds when D equals 2. So now I will give you the general result, which in the case D equals 2 is this result. So now don't be scared by this statement, which the only problem it has is that these are quantitative results, so you have to make the quantitative, you have to specify the quantities that you are bounding. So, but it's just telling you that if you have a set occupying very few residual classes in any dimension, then either your set is very small or it has strong algebraic structure. So let me now read you exactly what this means. You have two integers, k and d. D is the dimension, and k will be the exponent of the number of classes you occupy, so it's less than d, you occupy few classes. And just two real parameters. Then there is a constant that depends only on these parameters, nothing else, such that for any set that you choose that occupies less than p to the k residual classes, less than a constant p to the k residual classes, and for every prime p, in fact you don't need every prime p, just most primes p, then at least one of the following holds. Either S is small, S is less than n to the k minus 1 plus epsilon, and this is optimal, or S is strongly algebraic. There exists a non-zero polynomial of degree at most c, so uniformly bounded by the parameters, vanishing at almost all your set. And the coefficients also are n to the c, vanishing on at least 1 minus eta s points, almost every point, eta you choose. So this is telling you again, if you have a set that is very badly distributed, either you save a large power because this bound here saves a large power over what sieve theory tells you, and it is optimal, or your set has in fact to be the solution set of a polynomial equation. So, well, this is sharp and answers the original formula of the conjecture for every d greater than 1. And here we have no hypothesis for d, but when d equals 1, there is a further phenomenon very interesting that we don't know nothing about. But I will not discuss, but this is not the whole story when d equals 1. But for d greater than 1, this is the result, and in fact it's optimal because there are sets of this size that have very little algebraic structure. So this is the result. So now, turning into more recent events. Again, this is optimal, but one may be very unsatisfied because it's still a large power of n. I mean, what can you do if the stronger result is not true? But in some sense, one is dissatisfied, so I will talk about it in a moment. But first, let me just give you a very short summary of how the proof goes. This is just a very quick overview. You show that if the set is generic, whatever that means, it means your set is nice, it behaves nicely. Then there is some very small subset A in S, such that if a polynomial of low degree vanishes at A, it also vanishes at almost all your set. And this is a phenomenon that is also completely common when studying discrete algebraic structures. You can control your whole space by just a few points. And this is because if your set occupies very few residual classes, all the points are in some sense communicate very much with each other, much more than usual. You have very few residual classes with it. So you have very connected mod P for many primes P. So in fact, you can control the whole space by just a few points. And that if your set is nice. So the technical part of the proof is to show that actually if your set is large, so if your set is small, you're done. If your set is large, then in fact you have so many points that you can cut away the bad points and end with a very nice generic set. So if it is small, you're done. If it is large, you can make it look nice by just removing a few points. So, but once you have that, you have actually succeeded in controlling your whole space by a few number of points. So if a polynomial vanishes at these few points, it vanishes at the whole space. But then, if the set is very small, as it is, you can simply build by hand a polynomial vanishing at these points. For every small set, there is a polynomial of small degree vanishing at these points. And that concludes the proof, because if it vanishes at these points, it vanishes at the whole space. So that's how the proof goes. I later learned that this kind of thing has a name. It's called the polynomial method. And it's a very, very powerful tool that, again, exhibits this common phenomenon of discrete algebraic structure. For example, well, it is very much used in transcendental number theory. The results of Baker use polynomial method. And the result in Erdős distance problem was solved, I don't know, a few years ago using the polynomial method. And the Kakeya problem over finite fields was also solved using these methods. And in fact, there is progress being made on the Euclidean Kakeya problem using the polynomial method. And it's all problems in very different areas. So this is how the proof goes. And yes, now let me tell you what I was saying before. You have this theorem, but you are not satisfied because even if this is the best result, maybe it bothers you to have this big power of n here. So let's look at these counterexamples, why this is optimal. So for any epsilon greater than 0, it is very easy to give examples of sets that are very small, they have logarithmic size, and just using the Chinese remainder theorem or things like that, you can show that there are sets that are very small, of logarithmic size, that occupy only p to the epsilon residual classes for every prime. Then it is obvious that if you take you take a set in 3 dimensions, for example, and you take the first coordinate to be anything you want, any of the integers, and then the other coordinates belong to these very small sets. So of course, the second coordinate will belong to y, so they are only p to the epsilon residual classes, and the other coordinate will belong to z, so they are only p to the epsilon residual classes. So there are very few possibilities here, very few possibilities here, so your set will occupy few residual classes. So this is one example, but you say, well, listen, I mean, you immediately figure out what to do. I mean, you just say that your set has small sections, so that's the problem. You just get rid of that and you're done. But that's not true. Because take, for example, two polynomials f and g. So you take x in the first coordinate, anything you want. In the second coordinate, you take y multiplied by f of x. Now, the good thing is that polynomials preserve congruence classes. So if you know the class mod p of x, you automatically know the class of f of x mod p. So once you know x, you know the class of fx, you know the class of gx. So the only variation that happens here is given by the element y and the element z, and they occupy few residue classes. So again, this is another example of a set occupying few residue classes that it is big, because the first coordinate is anything, so your set is in fact big. So this is another example. It does not have small sections because your f and g are moving your sections around, so in fact this moves a little bit, but it still has some algebraic structure. But then, what you can do is take a large set of these very small ill-distributed sets, and you take the union of this construction over all these sets. So you take a logarithmic number of these things, you take the union of these constructions, and in fact you will see that this thing will also occupy few residue classes if you make appropriate choices. And it will be big, and the algebraic structure seems to be disappearing, because now you can take not only this, but any subset of this, and then how can you see the structure? But it is remarkable that in fact, this is, I mean, you try to play with this, try to make worse and worse examples, but you cannot do much worse than this. So this is another result, which says that you have a set occupying p to the kappa residue classes for every prime p and some real kappa. Before we needed the integer assumption, it was necessary, but now for this general result you need no assumption on k. This is just for any kappa, so any set, any number of classes that is small. Then you can always find some polynomial f of degree at most log n, and an exponent here, kappa over d minus kappa, vanishing on almost all your set. And this is, and in a sense, this proof is simpler than the previous one, and it is much more general. It's telling you that for any choice of the exponent, the kappa here, any choice, then if your set has few classes, you can always find a polynomial of degree, but that is very controlled, because you know, as I show you, it is false if you take a uniform bound. It is not true. But in fact, as you saw before, here you had something of logarithmic size. So in fact, that's the best you can do. You can in fact show that there will always be, if you have a set badly distributed in the residue classes, you can always find a polynomial of logarithmic degree vanishing at almost all your set. And that something like this should hold for integer values of kappa was conjectured by Green. And although his conclusion was a little bit different, but it has the idea. So, and it turns out that one can in fact prove this for any value, for any real value, and in fact get a logarithmic exponent, which one wouldn't have expected to get such a strong bound. So by the previous examples, nothing better than a power of a logarithm is possible here. So, so this is a very good example of how you can find discrete algebraic structures in problems that originally have nothing to do about it. You have this classical problem about distribution in residue classes, and the answer lies in these discrete algebraic structures. So let me finish with this last result. So, as I was saying, discrete algebraic structures are quite important. You can use the polynomial method or things like that to show that things that behave in a bad way are very algebraic. What it usually means is, for example, like in the previous case, that you can find some polynomial vanishing on this set. And then you turn to that leads you to a very natural question, trying to understand better, getting better uniform bounds for algebraic sets. So you know that you're assigning an object, you know if it behaves badly, it has to be very algebraic, but to get something useful out of that, you have to have strong control on this algebraic structure. And this leads you to one of the most basic classical problems of mathematics, which is to estimate the number of solutions of a polynomial equation, to give bounds for how many points can a curve have. So a basic problem is to estimate the number of, say, small rational solutions of an irreducible polynomial equation of degree d. That's a very basic problem, and we want estimates that are uniform over the choice of f. So we want an estimate that gives you can have only this many points, and this bound does not depend on the specific curve. Of course, results for specific curves are very well known, and there are a lot of results of that kind, but we want uniform estimates. So equivalently, you can see an irreducible projective curve of degree d. So it's just your curve of degree d is like counting rational points in an integral equation. And we want to obtain uniform bounds for the number of integer points of height less than d on this curve. So if you don't remember, the height of a point is something that is defined very simply. You just take the integer point. Here, you can always write this in a primitive way, that is that there is no natural number dividing all, different from 1, dividing all the coordinates, so they are all together, there is no common factor. So you write in the primitive form, the height is just the maximal size of these coefficients. So it's the very natural bound, so it's saying, so in fact, if you're counting points with height less than n, it's like counting rational solutions of size less than n. So this is a very classical problem, just how many points does a curve of degree d can have. So it is well known that if you take a rational curve, that is a curve of genus 0, it is well known that this quantity grows very large. In fact, this behaves, if you look at how many solutions does it have of height less than n, then you know that this quantity grows like n to the 2 over d, but the implicit constant depends on c. And in fact, if your curve is not rational, you have, for example, if your curve is of genus at least 2, you have Faulting's theorem that tells you that there are finitely many solutions. Well, you have, it doesn't matter. There are a lot of results also for elliptic curves, I mean, genus 1. So you have good bounds, but they all depend on the curve. I mean, for each curve, you know, Faulting's tells you it has finitely many solutions, but you don't know how many. So maybe if you're studying a discrete problem, you know it has finitely many solutions, but maybe the whole space is finite. So that is not very useful in that case. So what you want is uniform estimates. So this depends on C. So you know that you cannot have a uniform estimate that is better than n to the 2d because of rational curves. So the question is it true that for every irreducible projective curve of degree d, we have this sharp estimate? There are at most n to the 2 over d points in the curve, uniformly over the choice of curve. So no matter what your curve is, you can have at most a fixed constant time n to the 2 over d points. So the answer to the question is yes, so that will be the last result. And let me tell you some well-known results in this direction. Well, the result of Heath-Brown is very well known from 2000. He gives you a very strong bound that is very close to optimal. It tells you that for every epsilon greater than 0, you have that this quantity is bounded by n to the 2 over d plus epsilon. And this was inspired by the work of Bombieri and Pila in the affine case. Of course, this is very good result. The problem, of course, is that as epsilon goes to 0, the implicit constant, I mean, this is very standard notation in analysis, but maybe the audience is very broad. So this just means that it's less than a constant that depends on d and epsilon. So the number of points is less than a constant that depends on d and epsilon times n to the 2 over d plus epsilon. So the problem is that as epsilon goes to 0, this constant may grow to infinity. That's the reason why it does not give the result we were talking about. The sharp estimate, that is, you remove the epsilon, was obtained when d equals 2 by Browning and Heath-Brown. And that was the only case in which was known this sharp estimate. And Rolt has recently proven that it also holds for singular rational curves that define certain additional assumptions on the discriminant and the resultant. And there also work by Chong and Robert. There are other works, but for us, the most important partial results, most important results are due to, on the one hand, Ellenberg and Venkatesh in 2004, who prove something very interesting. You have your function, and you want to know how many solutions does it have. You have polynomial equation, you want to know how many solutions does it have. You want uniform bounds. But in fact, if you think about it, if the coefficients of your polynomial are very big, the number of values you can take, the image of this polynomial is much larger, because if the coefficient is large, maybe it can give you, these are homogeneous polynomials, so it gives you larger values. So it is less likely that it will give 0. If the coefficients are larger, you have a much larger scale of values. It is much difficult to get 0. So in fact, Ellenberg and Venkatesh show that that you have a bound that improves the larger these coefficients are. And they use this result to obtain this estimate that saves a power for curves of geometric genus at least 1. So I was telling before, if the genus is 0, that's the worst case, but if the genus is positive, then you expect less number of points. And in fact, Ellenberg and Venkatesh, they show that in fact you have a saving of this kind. Knowing how far you can go, in fact, one may expect that if genus is at least 2, you can get a logarithmic bound, so maybe we're very far from the truth. But it is a remarkable result, and it's a very interesting question to go how far we can go. But in particular, this gets rid of curves of positive genus in our problem. And the last result, which is the most important for us, well, both of these are very important, is the result of Sahlberger, 2010. And he developed something that is called a global determinant method, because before there were p-adic determinant methods, and now this is the global determinant method. And he used this to solve a conjecture of Sir about number of points on algebraic varieties, a famous conjecture of Sir. So he gave an answer to this question. And using these methods, he also managed to improve previous bounds and actually managed to give this bound for the problem we are talking about. He showed that the number of points on a curve is uniformly bounded by n to the 2 over d times log n. So this is very close to the truth, but still, the number of points can be much more, I mean, the logarithm diverges, so it's much more than what one expects. So yes, the final result of the talk is that in fact you have this sharp estimate. So the estimate that the number of points is less than a constant times n to the 2 over d holds uniformly over all irreducible projective curves of degree. So this bound is completely uniform, it is the optimal bound, and does not depend on the curve. So, and again, as I tell you, Ellenberg and Venkatesh showed that in fact this result, you can expect more if the coefficients are big. So, just this notation is just the size of the largest coefficient of your polynomial. And in fact, you have this improvement over theorem 1, which tells you that if you have a primitive irreducible homogeneous polynomial of degree d, I mean primitive just because you have to scale, otherwise this will be false, then for any curve of degree d, irreducible, you have this bound. So you have the bound before, n to the 2 over d, but now this gives, you lose a logarithm, but you save a power, so you always gain, you always win. So you actually can save a power of the largest coefficient over the bound. And this, again, is completely uniform on the curve. So this constant here does not depend on the curve. The coefficient depends, but it's good. You're saving the size of the coefficient. So this is the same result again. And this result is deduced from a more general result that has to do with hypersurfaces in arbitrary dimensions. So you get a bound of that kind for any hypersurface in any dimension, not for a number of points, but for something very similar, which in particular gives you this result. The bound for general hypersurfaces also improves with the coefficient, so it's nice. It refines previous results for hypersurfaces. And the ingredients of the proof include this method of Sahlberger, which is very powerful, this global determinant method, but we employ it in a quite different way. In particular, we make use of results of von Bier and Baller on systems of linear equations of the integers, a very nice result of von Bier and Baller. And taking these things together, we can actually give this uniform bound. So, well, let me end the talk here, and I hope I have given you some idea how these discrete algebraic structures work. Thank you very much. Yes.
That if your set S occupies few residue classes mod P, then it's either very small or very big. And I'm just wondering if there's some kind of standard for the word few, it's very big. Is there something like?
Well, yes. These are the precise statements, right? Take any, the first statement is, there were two results. The first result is if you take any integer k less than d, and here few will correspond to less than a constant time p to the k, which is in fact the optimal assumption you can make, because if you make less assumption than that, for example, if you take a real number, then you have these strange sets that do not satisfy this. But in general, you can take anything. You just take any kappa you want, not integer, any real. So your few will be less than p to the k, to the kappa, for any kappa you want, so it's just a dimensional anything less than d. Then, in fact, you can have a polynomial of degree n most log n vanishing on the set. Thanks.
Any other questions? If not, let's thank Miguel for time.
Thank you.